All right, let's look at number 2 and number 3 together. What is the formula for the compound sulfur 2 chloride? So this is in a stock name, but notice that this isn't the typical stock situation because this is a nonmetal and a nonmetal. Okay, and so usually when we talk about names for nonmetals and nonmetals bonded together, covalently bonded molecule, we're talking about the prefix system. Typically, we'd have a di, a tri, a mono, something like that. But this is using the stock system here. This is using the stock system, which you can do. It's just that we're not going to do that all that much in this class because that's not typically how we name those types of compounds. But what this Roman numeral is telling us is that this sulfur here is having a +2 oxidation state. This is a +2 oxidation state, and so that means that this chloride here needs to have an overall -2. Now, I know that chloride has a -1 charge, so in order to accomplish this -2, I need to have 2 of them. So I'll go sulfur, 1 sulfur, 2 chlorides. So the prefix system name here would be sulfur dichloride. Moving on to B, what is the stock system name for NO2? Now, the prefix name would be nitrogen dioxide. Okay, it's actually also a polyatomic ion as well. Actually, it's not an ion. This is just equivalent. Never mind. Forget that. Anywho, what is the stock system name for NO2? Now, there are two oxides here. There are 2 oxides here, and since we don't have any of the special situations that are going to make oxygen something other than -2, we assign it a -2. There are 2 of them, so that's a total of -4. And we don't have an overall charge here, so we know that this single nitrogen needs to balance that out completely with a +4. Now, in the stock system name, that Roman numeral is going to be the oxidation state of that first element. So, nitrogen 4, oxide. All right, 3A. Use electronegativity values to determine the one element that always has a negative oxidation number when it appears in any binary compound. So what we're doing here, if we think about conceptually what an oxidation number is, we're trying to find the element that is going to draw other electrons more strongly than any other element. And that's the same question as what element has the largest electronegativity value. Hopefully you guys know already or remember that that is fluorine. Fluorine has a 4.0. It's the largest number on this electronegativity scale, on this Pauling scale. And so there are no elements that will pull on electrons more strongly than fluorine. So that means that fluorine is always going to successfully attract an electron. If it's attracting an electron, the electron is getting closer to it, making it negative, making it having a negative oxidation state. So, with that in mind, we just use electronegativity values, fluorine coming in with that big old 4.0, to determine the one element that always has a negative oxidation state. We just agree that is fluorine. Now, moving on to B, I do want to point out this part, when it appears in any binary compound. There is a special exception in which it doesn't have a -1. What is the oxidation number and formula for the element described in part A, right here? So we're talking about fluorine. So what's the oxidation number and formula for fluorine when it exists as a pure element? Well, there are a few things that we're wanting to point out here. One is that our special circumstances, pure element. Okay, pure element, that is one of our special circumstances. That is what this question is asking for. Got a picture a little crooked. And so we need to look at fluorine as a pure element. Before we talk about the oxidation state, let me remind you that Brinkelhoff identifies the diatomic molecules, and so that tells us that fluorine is going to be F2. F2. Now, right now, fluorine isn't with anything but fluorine. right? So that oxidation number isn't going to be -1 because it's not like fluorine pulls more strongly on those electrons than fluorine. It's the exact same strength. And so none of those electrons are going to move towards one fluorine or the other because they're being pulled on with the exact same strength. And so that is going to result in an oxidation number of 0 because it's a pure element. And that's why we have that special circumstance of a pure element.